Hi to everybody. In this lecture video, we are going to be dealing with chapter 27. And chapter 27 is about the current and the resistance. Now, after doing this chapter, you will be in a position to define electric current, current density, and the Ohm's law. You will also be able to derive the expression for the trip velocity of charge carriers, and you will also be able to derive the relationship between resistance and resistivity, and you will also be in a position to discuss the superconductivity, and you will also be able to derive an expression for the rate of conversion of energy in an electric current and Joule's law for thermal energy dissipation in a resistor. And lastly, you will also be expected to solve the problems on the above. Now let us just start by defining the electric current. The electric current is the rate of flow of charges through some region of space, and the SI units of the current is amperes, and we use A to denote the amperes. Now 1 amperes is equals to 1 kiloohms per second, and we are using the I to denote the electric current. Now just assume that charges are moving perpendicular to a certain surface area A, and if those charges are positive charges, because positive charges are pointing in the same direction as the current, therefore the current will also be pointing in the same direction. Now in a case where a small amount of charge, say a change in Q, is an amount of charge that passes through that surface area at a change in T, then the average current is therefore given by this equation as change in Q divided by the change in T. Right, now if the rate at which the charge flows varies with time, the instantaneous current I can be defined, or it can be found by using this equation. What does this mean? It means that the charge will just be a function of the time. Therefore, whenever you want to get the current, you do the first order differentiation of that Q as a function of T, then that will be your instantaneous current. Right. Now, the charges passing through that area could be positive or negative or both. It is conventional to assign the current the same direction as the flow of positive charges. The direction of the current is opposite to the direction of flow of electrons or negative charges. It is common to refer to any moving charges as charge carriers. Now, from now onwards, you will be hearing me talking about the charge carriers. Right. Now the charged particles move through a conductor of a cross-sectional A. The cross-sectional A of that conductor is this A. Now, if this is a cross-sectional area of that conductor and changing X is the length of that conductor, therefore the volume of that conductor is just going to be A times the changing X. Now in this case, N, when I define N is the number of the charge carriers per unit volume. N is the number of charge carriers per unit volume. Now, if I want to write that small n, that the small n is equals to the number of charge carriers, I will just denote it by n subscript C per unit volume. But I know what is the volume. The volume of that is just NC, number of charge carriers, divided by volume is just area times change in X. Therefore, from this equation, if I want to write the number of charge carriers, it will just imply that the number of charge carriers can just be determined in terms of N times A times change in X. So that is the equation that you are seeing here. That is the total number of the charge carrier is therefore determined by that equation. Right. Now, if we know that this distance, when these positive charges are moving from here to there, we can denote that distance as a function of the velocity and time. Why? Because if we know the velocity that these charges are moving at, and then we can just use the the equations for the displacement, because we know what is the displacement. The displacement is always defined in terms of the v times t. Now in this case, therefore, that is what you are going to have. But before you can even do that, let us just try to find the total charge Q. The total charge Q will just multiply this number of charge carriers by Q. Now the total charge will just be given by this equation here. Now the drift speed at which the charge carriers are moving at is just given by this equation from the previous figure. And the change in x, of course, we have seen that it is the drift speed times the change in t. Now if we know what is the change in x from this equation here, we just gonna take that and plug it on that equation. Therefore the total charge is just given by this. Why are we doing the total charge? Because we want to get the average current, because we know that the change in Q divided by change in T is nothing else but it's just the average current. Now we know what is the average current. Now if we plug the average current in that equation, this is what you are going to have, because this T will cancel with that other T. Now the average current in terms of the drift velocity and the Q and N and the area is just given by that equation there. Now suppose that this negative charges are moving inside your conductor. Now if the electric field is in this direction, therefore the drift velocity will be in that direction if these charges are negative charges. Now the zigzag lines represent the motion of charge carriers within the conductor, because they are not going to be moving very smooth. They will just be colliding with the materials or with the atoms of that conductor. So that's why you are seeing this movement of these zigzags of motion. Now the net drift velocity is small. Now the sharp changes direction are due to the collision. As I've said, the net motion of electrons is opposite the direction of the electric field. Yes, I mean if the electric field is going in that direction, therefore the drift velocity for these electrons or negative charge is going to be on the other direction. Right, in the presence of an electric field, in spite of all the collisions, the charge carriers slowly move along the conductor with a drift velocity Vd. Now the electric field exerts a force on the conduction electrons in the wire. The force causes the electrons to move in the wire and create a current. Right, the electrons are already in the wire. They respond to the electric field set up by the battery. Now the battery does not supply electrons. It only establishes the electric field, which in return establishes the force on these charge carriers. Right, now let us just do the following quick quiz. Now consider positive and negative charges of equal magnitude moving horizontally through the four regions shown in the figure. Rank the current in these four regions from the highest to the lowest. As we have said that if the equal magnitude, for example, if we start with this one, if I have two negative charges, that is just equivalent to two positive charges but moving in the other direction. Now for this figure in C, you have two positive charges plus the other two positive charges, but the positive charges are moving to your right while the negative charges are moving to your left. Now this is the same as in this situation, but in this situation the direction the holes or the positive charges are moving in the left direction. So in this case, for this one, this is just equivalent to the four positive charges. All right, now the last one is, this one is therefore equivalent to 5 positive charges. As a result, when we rank current, we just look at the number of positive charges that we have in all. Therefore, with this, when you rank this is just going to be equal to that. The current there will just be equal to that, but this one will be less than that, and this for this will just be less than that. Now, as a result, this is what you are going to have for that quick quiz. Now let us also do the drift speed in a copper wire example. The 12 gauge copper wire in a typical residential building has a cross-sectional area of 3.31 times 10 to the minus 6 meters squared. It carries a constant current of 10.0 amps. What is the drift speed of the electrons in the wire? Assume each copper atom contributes one free electron to the current. Now the density of the copper is just given. Now if you know the density of the copper, and from the Avogadro's number, you remember that 1 mole carries the Avogadro's number of atoms. Now the Avogadro's number, if you still remember, is nothing else but it's just a constant given by 6.02 times 10 to the power negative 23 per mole. Now this is 1 mole. Now in this case, the n, our n in this case, it will just be the Avogadro's numbers divided by the volume. Right. Now from there we can we know the atomic position of the copper, and then we know the molar mass. Therefore we are just going to solve that with using the periodic table, and we know that in periodic table the copper is position number 29, and the molar mass is just given there. And in that case we just have to convert this molar mass into the kgs per mole. Now from this equation of the density, we know that the volume is just equals to the molar mass divided by the density. Now the number of the n in this case is related to the Avogadro's number divided by volume, but we know what is the volume from that equation. If you plug the volume, this is what you are going to have for that equation. Now from the average current, we can be able to rearrange that equation and write the drift velocity in that case. Now the average current is nothing else but it's just that current that is going to pass through. In that case, when you replace n with this that you have there, then this is what you are going to have. And in this case, you all have these values for each symbol in this case. Now if you plug the values, the drift velocity is just going to be given by 2.23 times 10 to the power minus 4 meters per second. Right, look at the molar mass. The molar mass, because in the periodic table, is in gram per mole, therefore it must be converted to kilograms per mole. Right. Now let me also introduce you to the current density. Now current density is nothing else, is just J is just given as the current divided by A. And of course the units for the current density is nothing else but is just A per meter squared. Right. Now that is the definition of the current density in short. Now, but from the previous equation we were able to derive the current, and then we have seen if you plug the current there, this A will cancel with the other A on the equation of the current. Now as a result, the current density will just be given by this equation there. Now this expression is valid only if the current density is uniform and A is perpendicular to the direction of the current, and the SI units, as I have said, is just given by this. Now the current density is in the direction, note that the current density is a vector, it is in the direction of the positive charge carriers. Right, let us also talk about the conductivity. A current, density, and electric field are established in a conductor whenever a potential difference is maintained across the conductor. Now for some material, the current density is directly proportional to the field. What does that mean? It means that the current density is always proportional. The current density is always proportional to the electric field. Now if I write it in terms of the vector form, this is what this statement is saying. But in order for us to have equal sign there, it will just be J is equals to a certain constant times the electric field, and now this constant is what we call the conductivity. By the way, this equation that you are seeing here, this is what we call the Ohm's law. This is the equations for the Ohm's law. Right, now that's the constant of proportionality there is nothing else but is what we call the conductivity, and it is denoted by this symbol, which is sigma. Right. Now, in that case, as I've said, I also want to introduce you to Ohm's law. Ohm's law states that for many materials, the ratio of the current density to, you remember I told you that this is the Ohm's law is the conductivity times the current density is the conductivity times the electric field. Now, the Ohm's law states that the ratio of the current density to the electric field is nothing else but is equivalent to a constant, because I have to divide it by E. If I write this E here, therefore I must cancel this other E here, and that constant is what we call the conductivity of this material. Now, most of the metals obeys the Ohm's law, which is this equation here, as I've said. But it is also important to note that some materials obeys the Ohm's law, and those are the materials which are said to be ohmic. For example, we normally call them the ohmic conductor. However, there are some materials which are not obeying the Ohm's law, and those materials are what we call the non-ohmic materials. Now, Ohm's law is the fundamental. Ohm's law, is not a fundamental law of nature. You cannot compare the Ohm's law with, for example, the law of nature, such as the gravitational law or the Coulomb's law. Why that is the case is because Ohm's law is just an empirical relationship valid only for certain types of material. It is not valid for all type of materials. For example, if you take the insulators are not obeying the Ohm's law, right? Now, and this Ohm's law was actually formulated by the German physicist known as George Simon Ohms, and then he discovered the proportionalities now known as form of the Ohm's law. Good. Now, for example, suppose that you apply the potential difference between this wire, and the electric field is going in that direction, and when the current is going in that direction. Now, from the previous chapters, we have seen that the electric field can be determined in terms of the gradient of potential. The gradient of potential. Now, if I want to write the change in V for this equation, this is what you are going to have for the change in V for that equation. But now we know what is the electric field, because electric field from the Ohm's law, the electric field from the Ohm's law, the magnitude of the current density is just given by that. Therefore, this implies that the electric field is nothing else but is just the current density divided by the sigma. Now, from that equation here, the change in V is equals to EL. Now, whenever I see E, I'm just going to write this. Therefore, that equation just becomes J divided by sigma times L. Right. But we know what is J. We also know what is J. J is nothing else but it's just the current density, I divided by area. As a result, this equation will just be written in terms of whenever I see J, I'm just going to write this. Therefore, that is just going to be I over A times sigma, but that must be times L. All right, that is the case. But now if we take this as a constant, and we name that constant the the resistance R, that will just be your resistance. Therefore, the change in V will just be equals to I times R, where R is just the constant of proportionalities. Therefore, that means the resistance is nothing else but the resistance is just equals to L L times A divided by A times sigma. Right. That's what I am just trying to summarize for this slide. Now, in that case, this is what you are going to have from as I've shown you that. And when you rearrange that equation, this is what you are going to have for R is just given by changing V divided by I. Now, the constant of proportionality is what we call the resistance. Now, resistance in the circuits arises due to collision between the electrons carrying the current and the fixed atoms inside the conductors. Now, the units for resistance is denoted by this symbol, and this symbol we call it ohm. And 1 ohm is nothing else but it's 1 volts per ampere. Right. Now, let us also talk about the resistors value from the coding. For example, when you look at these circuits here, you can just see there are many resistors there. There are many resistors, and this the colors for these resistors are actually different. And these colors in your resistors, they are actually denoted. They are actually giving us the information on the magnitude of the resistance. For example, this is a table where if you have black, for example, it's 0. If you have red, this is 2. For example, let us just do this kind of resistors that you are seeing there. Now, if the first color here from my left is red, therefore that will mean that is 2. The first number is 2. Now, the second color is blue, it's 6, which means the first 2 numbers is 26. And the third color is just a multiplier, 10 to the power what? Green is where is green? Green is 5. Therefore, the multiplier is 10 to the power 5. As a result, the value for this resistance is nothing else but it's 26 times 10 to the power 5 ohm. And the last color refers to the resistance tolerance, resistor tolerance. And in this case, if it is the silver, it is just 10%. The tolerance of that resistor is 10%. And this is the stuff that you have already done in your online experiment. Right. Let me also introduce you to what we call the resistivity. Now, from the Ohm's law, which is nothing else but it's just the conductivity times the electric field. Now, this is what we call the conductivity. Now, the inverse of this conductivity is what we call the resistivity, and resistivity in that case is determined by this symbol rho is just equals to 1 divided by the resistivity. Now, I must also mention that you should not be confusing this resistivity with the volume charge density, because you remember in the Gauss laws chapters, and we were just saying this is just the volume charge density. I'm very sorry because in your book this symbol is being used for both, but please be very careful of on which context are we talking about the rho. So this is totally different thing in this case of ohm. So that is the resistivity, right? That's very important because many students sometimes are getting confused of that. Now, if I want to write the units of the resistivity is nothing else but is ohms meter. Now, resistance is also related to this resistivity in terms of this equation. You remember that the resistivity, the resistance, we find resistance as equals to L times sigma A. But now we know what is 1 over sigma is just equals to rho. Therefore, the resistance can just be written in terms of L times A divided by area. Therefore, this is the relationship between the resistance and the resistivity, right? And you can also see that the resistance is directly proportional to the resistivity of the material. That's this in summary. Good. Now, you've got different values for the resistivity, and of course the resistivity or resistance of a material is a property of a material. For example, different materials have different resistivity. they've got different resistivity. For example, if you take glass is just ranging from these values, and for example, the gold is 2.4 times 10 to the power minus 18. Let us just also look at the copper. The resistivity of copper is just given by this. And you also have the temperature coefficients, but I will just introduce you a little bit later about the temperature coefficients. Those are the property of the material used to develop that resistor. Right. Now, every ohmic material has characteristic resistivity that depends on the properties of the material and on the temperature. Of course, I mean, a very good example is that one of the silicon wafer. You remember in that YouTube video, that silicon wafer is not conducting the electric current up until it is being heated. Therefore, the resistivity is also a function of, is a property of material as well as the function of temperature. It depends on the temperature. Now, resistivity is a property of a substance, as I've said. The resistance of a material depends on the geometry and its resistivity. Resistance is a property of an object. An ideal conductor will have zero resistivity. Now, however, the ideal insulator will just have infinite resistivity, because insulator doesn't conduct the electricity, therefore it will have the infinite resistivity. Now, for those materials which are obeying the Ohm's law, this is what you are going to find for the materials which are obeying the Ohm's law. Now, from that equation, I just want to remind you that change in V, this is just the result of the Ohm's law, is just given by IR. These are the results of Ohm's law, but the Ohm's law is nothing else. Ohm's law is just given as the current density is equals to sigma times E. Now, from that equation, if you plot your I on the, if you want to plot I in your x-axis, therefore this equation, I can rearrange that equation and write it in this fashion. I is equals to change in V divided by R. Now, if you plot y in the I in y-axis and then you plot change in V in x-axis, this is nothing else but is just equivalent to a straight line graph. That is y as a function of x. Of course, y as a function of x is nothing else but it's just mx, and we don't have c because this graph is passing through the origin. Now, if you equate that to this equation here, this is what you are going to have. This I is in your y-axis, and the slope is just going to be, your slope is just going to be 1 over r. That is just going to be 1 over r. That is going to be a slope, while your x, it will just be related to the change in V. Right. Now, as a result, you can just see when you plot that graph, the slope, the m for that graph is just nothing else but it's just going to be 1 over r. Right. That's what I am actually trying to say about this. But this is only for ohmic materials. Let us just see for non-ohmic materials. For non-ohmic materials, this relationship is non-linear. It's not linear. Now, it is not linear. For example, a very good example of this is just a junction diode. Is a very good example of non-ohmic devices. Right. Now, maybe I must also say something about that this equation here. The change in V is equals to I times R. Now, suppose that I am plotting the change in V in Y, and then I am plotting, if I'm plotting the change in V in y-axis, change in V in y-axis, and then I'm plotting the current in x-axis. Therefore, in that case, the equation can be rearranged like this. Change in V is nothing else but it just equals to R times I. Now, this is Y, and then this is just mx. Therefore, the slope there will just be the resistance. But if you switch this, two, and you put this one in this x-axis, and then you put that on this axis, on the y-axis. Therefore, the slope in that case, when you switch them like previously, therefore the slope is just going to be 1 over r, as I have already shown you, and that's what you were supposed to do in your online experiment that we have already performed in the previous 2 weeks. Right, let us also do the following quick quiz. A cylindrical wire has a radius r and a length l. If both r and l are double, does the resistance of the wire increase, decrease, or remain the same? Now let us just write the equation for the resistance. We know that the resistance in terms of rho times L divided by A. Now what happens if you double the length and the radius? Now the wire is actually taken as a cylinder, for example. Now this is the area that we are talking about there. The cross-sectional area that we are talking about of that wire is this one. Now it has a certain radius A. Therefore we can be able to tell what is the radius. In that case, this equation will just change to rho times L divided by 2 pi r squared, because that is the radius. Now you see, if you double the length and the radius, this is what is going to happen. If you double the length, you are going to have a factor of 2 here, but if you double the radius, you are going to have a factor of 4. You just have a factor of 4 there. Now as a result, what is going to happen to the resistance, because this 2 will just cancel that other one, the resistance will therefore increase by a factor of 4, will then decrease by the factor of 4. Right, so that's therefore the correct answer for that is just that the resistance will decrease by a factor of 4. Now let us also do this quick quiz. In the figure, as the applied voltage increases, does the resistance of the diode increase, decrease, or remains the same? Now in this case, remember, as I've already explained to you, now you've got this graph here, and then you've got, in this case, you've got change in V, and then you have I in this y-axis. Now the graph just goes like that. I'm sorry for not being able to draw it straight, but now if you look at the slope of this graph, if say you start from here at the origin, you just go direct to some point there. Now the slope there, as I've already shown you, the slope of this graph is just going to be given by 1 over r, and you can see that as long as you that is just going to be for this value of the change in V. Now let us just take another slope higher, so you see now, if I go up, if I am actually increasing what you call the change in V, that is going to be this way, the slope will also be increasing of that graph. Now if the slope is increasing, remember, from the slope is nothing else but this is just equals to m. M is equals to 1 over r. Therefore, do you see that the slope, the m, is inversely proportional to 1 over r? When the slope increases, the resistance is going to be decreasing. Now, as a result, the answer for that quick quiz must definitely be B. Must be B. Right, now let us also do the following quick example. The resistance of a nichrome wire. Now we are given the radius of a nichrome wire to be 0.32 millimeter. Calculate the resistance per unit length. Now the resistance per unit length, from that equation, the resistance per unit length, now the resistor is just equals to rho times L divided by A. But if I have to calculate the resistance per unit length, then I'll just have to write L here and then cancel there. And then you know the values, you just plug those values in your equation, and then you calculate the resistance per unit length, and the answer for that is just going to be this. However, in this table, you will just look at the nichrome. Where's the nichrome? Nichrome is just given as the resistivity value of the nichrome is there. All right, now that's why you see this value in there. Now in the case of the test and exam, you will be given a table, or you'll be given the value of the resistivity. Good. Now the part B of the question: if the potential difference of 10 volts is maintained across 1.0 meter length of a nichrome wire, what is the current in the wire? Now you know the potential difference, and you will just multiply by the resistance per unit length with L, and then you will get the current as 3.2 amperes. Let us also do the following example of a coaxial cable, which are used extensively for cable, television, and other electronics application. A coaxial cable consists of two concentric cylinders, conductors. The region between the conductors is completely filled with the polyethylene plastic, as shown in the figure. Current leakage through the plastic in the radial direction is unwanted. The cable is designed to conduct current along its length, but that is not the current we are being considering in this problem. Now the radius of the inner conductor is just given by that value, and the radius of the outer is just 1.75 centimeter, and the length of the coaxial cable is 15.0 centimeter. The resistivity is just given. Now calculate the radial resistance of the plastic between the two conductors, and we are also going to apply the same. The resistance is just nothing else but it's just the rho times L divided by A. But in this case, we are not considering the resistance in the direction of L, but we are considering the radial resistance. As a result, this equation will just change to be rho times R divided by A, and then we know what is the area is of a cylinder. Therefore, that's the approach that we are going to be using to solve this problem. And we just have to take the integration from A to B. And now in that case, this is what you are going to have. If you take the small amount of resistance in the radial direction, you will just have to take a small portion of this radius, and you integrate from A to B. Now, if you do that, all these are just constant. You are just going to be integrating the 1 over r dr. And I just want to always remember you that, to remind you that the integral of 1 over x dx, integral of 1 over x dx is nothing else but is the natural log of x plus c, since we don't have the integration limits there. Now, if you apply the same procedure for the integral of 1 over r dr, this is what you are going to have, and then you put the integration limits, this is what you are going to have, and this is actually your answer for the resistance. And now you know all the constant, now you know all the symbols in your equation, then you can just plug, and then the resistance of that coaxial cable is just going to be 1.33 times 10 to the power 13 ohms. Now let us also talk about the resistance and the temperature. Now, over a limit of range of temperature, the resistivity of a conductor varies approximately linearly with the temperature. What does that mean? If the temperature increases, the resistivity also increases. Now the P naught is resistivity at the some reference temperature, for example T naught. T naught is usually taken to be 20 degrees Celsius. Now this alpha is what you call the temperature coefficient of resistivity, as I told you earlier on that I will introduce you to this. This is the temperature coefficient of a resistivity, and the SI units of the temperature coefficient of resistivity is nothing else, it's just per degree Celsius. Now, because of the fact that the resistor is directly proportional to resistivity, from that equation R is equals to rho times L divided by A. The resistivity from the previous slide, it can just be replaced by the resistor, and now all the other terms will just cancel, and then we can be able to see that R is just given by this equation. Now that's what you are going to have, because R and resistivity are directly proportional to each other. Now we use this property enables the precise temperature measurement through a careful monitoring of the resistance of the probe made from a particular material by just using this equation there. Right. Now, resistivity as a function of temperature, the resistivity as a function of temperature, you can just see that it is almost linear. But however, when you come closer to when the temperature is low, that the linearity is actually being, the relationship is no longer linear. Now, the resistivity usually reaches some finite value as the temperature approaches absolute temperature. For example, if you zoom at that point, you see this is no longer linear. As a result, that is your P naught on that equations that I've just discussed with you. Right. Now, the residual resistivity near absolute zero is caused primarily by the collision of electrons with impurities and imperfection in the metal. High temperature resistivity is predominantly characterized by the collision between the electrons and the metal atom. Now, this is linear range on the graph. Now, let us also do the following quick, and it is about this the incandescence light bulb. Now, the question is just asking, when does this bulbs carries more current? Now, to answer that, we just have to go back to that equation of R is equals to R naught plus 1 plus alpha times T minus T naught. Now, in this case of this incandescent light bulb, what is going to happen when this light is at room temperature? At room temperature, the resistance will just be low. And I also want to remind you about the results of the Ohm's law, that is V is equals to IR. Now, do you see that the relationship between the current and the change in the R is actually inversely proportional, because I can write R here and then I will definitely delete this other one there. When the filament of this light bulb is at room temperature, the resistance is low, and if the resistance is low, the current is high. But the moment the temperature increases, when the filament is heating up, therefore the resistance is high, and when the resistance is high, it will mean the current is low. As a result, immediately after you have switched on the light bulb, the current is more. In fact, maybe this is one of the reasons. In fact, that's the reason why most of these lights will just fail immediately when you switch them on. And this is one of the good reason why sometimes when you are switching on your light bulb. I mean, we used to use this light bulb before the LEDs. Now, what is happening actually, the current is very high, and that causes a stress on your filament. As a result, it mechanically fails. It just failed, and the connection there is lost. As a result, the light is burned off. Right, that's the main reason for that, and then the answer for that is just that A. Right, the semiconductors are materials that exhibit a decrease in resistivity with an increase in temperature. Now, alpha is negative. There is an increase in the density of charge carrier at the higher temperature. Let us also talk about the superconductors, a class of materials and compounds whose resistance falls to visually zero below a certain temperature, which is called the critical temperature. Now, the resistance as a function of temperature. Now, the resistance here is just zero after reaching that critical temperature. The graph is the same as normal metal above the critical temperature, but suddenly drops to zero at Tc. Now, the value of Tc is sensitive to chemical composition, pressure, and molecular structure. Once a current is set up in a superconductor, it persists without any applied voltage, because R is equals to 0 for the superconductor. There's no resistance, or resistance is equals to 0. Now, the application of these superconductors is they are applied in many fields. For example, the the magnitude of the magnetic field is about 10 times greater than a normal electromagnet, and then it is also being used in MRI units in your hospitals. Now let us also talk about the electrical power. Now, when you consider this electric circuit here with the one resistor and then the potential difference, now in this case, when the switch is closed, as the charge moves from point A to B, the electric potential energy of the system is changed by this change in V. Now, the chemical energy in the battery must decrease by this same amount. Now, what will happen when it passes C and D? Now, as the charges move through the resistor C to D, the system loses the electrical potential energy during collision of electrons with the atoms of the resistor. Now, this energy is transformed into internal energy in the resistor, corresponding to the increase in vibrational motion of the atoms in the resistor. As a result, the resistor will just heat up and loses that energy as the heat radiation. Now, the resistor is normally in the contact with the air, so it increases temperature while will result in the transfer of energy by the heat into the air. The resistors also emits thermal radiation, of course, because it is getting heated because of the collisions inside these charged particles and the atoms inside your resistor. After some time interval, the resistor reaches a temperature. The input of energy from the battery is balanced by the output of energy by heat and radiation, as I've said. The rate at which the system loses the potential energy of the charge passes through the resistor is equal to the rate at which the system gains energy in the resistor. Now, the power is the rate at which the energy is delivered to the resistor. Now, which means the P is just given by the rate of the change in electrical potential energy. And we know what is the change in U. Change in U is nothing else but is Q change in V. And then if we write dQ change in V, but we know what is dQ, the rate of change in charge, is nothing else but is the current from the previous slides. Now we can just see that the power, therefore, the power is just given by I times change in V. But we know from the Ohm's law results, change in V is equal to IR. Now, whenever I see change in V, I'm going to write that. Therefore, I will just have I squared times R if I plug the change in V by this equation. Right. Now, for the same equation also, I can also write this thing in terms of whenever I see I, I'm going to write the change in V divided by R. Now, if I do that in this equation, I'm just going to have change in V squared divided by R, because that change in V will multiply with that other one, and then you've got the resistor there. What does this equation imply? This equation implies that if you know the current and the potential difference, this is what you are going to use. But now, if you know the potential difference and the resistor, this is the equation that you are going to use. But if you know the current and the resistor, this is the equation that you can use to calculate the power of your. Right. Now, in that case, this is what I've just shown you now. Now, the I is the current and it is in amperes. The R is the resistance, it is in ohms, and the change in V is the volts. The change in the potential, the difference in is units is volts, and the P is the power, and the power is calculated in watts. Right. A single electron is moving at a trivial velocity in the circuit. It may take hours for an electron to completely around the circuit. The current is the same everywhere in the circuit. Current is not used up anywhere in the circuit. The charges flow in the same rotational sense at all points in the circuit. Now let us just do this example as our last as our second last. An electric heater is constructed by applying a potential difference of 120 volts to a nichrome wire with has the resistance of this. Now if you have to find the current from this equation and the power rating, therefore you just use that equation of the Ohm's law, 120 divided by 8, and then you just punch your calculator, and then if you have to calculate the power Now you know that the power is just given by I squared. The result for 120 divided by 8 is nothing else but it's just 15.0 amperes. Now as a result, your power is just going to be given by 1.80 times 10 to the power 3 watts. Now, what happens if the potential difference is doubled? Now remember, in the previous example, the change in potential difference was just given by 120 volts. Now in this case, what is happening if the change in V is doubled, because it's now 240? What happens to the current? Now I just want to remind you that these are the equations that I'm going to use to solve that problem. Now, if I have change in V is equals to IR, therefore if I double, and I know what is power is just given by I squared R. If we assume that the resistance is constant, now if I double the change in V, it will mean that I am also doubling the current. Now if I double the current, do you see what is going to happen to power? Power will just be 4 times the initial power. Right, that will be the answer for that question. Right, now let us just also link electricity and thermodynamics. And emission heater must increase the temperature of 1.50 kg of water from 10 degrees to 500 degrees Celsius in 10 minutes while operating at the changing 110 changing volts. Now, what is the required resistance of the heater? Now, the required resistance of the heater, we know that the power is just given by this. And then from the thermodynamics that you have done in your first semester, the Q is nothing else but it's just MC change in T. Now, if you rearrange this equation, this is what you are going to have. And now you know all the values, then you just plug the values, and this is what you are going to have in terms of your resistors, 28.9 ohm. So good people, I would like to pause here, and these are the problems that you have to do for your practice at home. And I also want to explain that the change in V, the results of Ohm's law, IR, this is just the results of the Ohm's law, J is equals to sigma E. Now, to make this equation make sense, what is happening there, I have also shown you this cartoon here, so that you can also be able to see what is happening. The volt, or the potential difference, is trying to kick or help the current to flow through the conductor. But what is happening with this guy, the ohm, the resistance is trying to resist that flow of these charges. So this is what you have to picturize your change in V is equals to IR. Good people, with that, I would like to pause here and then see you next time, and goodbye.